Hello, everybody. Today we're going to deal with a program or the issue of how to model and design an impedance network for our antenna on our satellite. So we're going to start with a program called EasyNet 5. And I have pre-entered the elements, and we're going to take a look at this antenna. So we're going to model this antenna by a ground plane that's essentially 4 inches and a monopole that is 8 inches. And they're tied together at this point, and we're actually going to feed them at this point. Now, one of the neat advantages of this program is that we can sweep this antenna over a range of frequencies, and today we're going to sweep it from 400 megs to 500 megs. And I've done that, and I've recorded that on a PowerPoint slide. Let me switch to it here. So what we've done is we've actually modeled a ground plane of 4 inches and a monopole of 8 inches. And we've swept this antenna, and at the resonant point it yields an impedance of 86 minus J72. Let me show you the plot as we sweep it, and when we click on this thing, here's where we get the impedances at this point. Now, let's bounce out of this thing, and now let's start to hook this thing up to our radio. So we actually have a PC board that connects the antenna to a connector which goes to the radio, and that is depicted in this drawing here. So this terminal is where the monopole, 8 inches, extends out. Piece of wire extends out here 8 inches, and here's where it connects into the frame of the satellite. Now, what's interesting is to note is that between where the antenna connects and the connectors, there's actually some physical difference. And this, as we've modeled this to be a feed line. And to do that modeling, we go to a program called AppCAD, which is this program here. So the PC board will have a LAN carrying the signal. It will have 2 pieces of ground plane on each side of it, and the thickness of this board is 62 mils. All of these dimensions are critical, and what they do is these dimensions are modeled as a transmission line with a characteristic impedance of 50 ohms, roughly 50 ohms, and the phase velocity, because of this dielectric constant, is actually, the wavefront is actually slowed down 0.58 times the speed of light. In effect, although physically our transmission line is only 1 inch, electrically it is 1 inch divided by the phase velocity, or approximately 1.7 inches. So let's go figure out how to do a match section. Well, one of the programs that I like to use is a Smith chart. This one is called QuickSmith. And what we do, let me just show you how nice this works. So we're gonna design a match network. We're gonna actually today use an L match, and I'm gonna set these to 0 just to give you an idea how neat this is. So to review our circuit, here's our antenna right here presenting some impedance. It is offset by a feed line that is 1.7 inches. And now we're going to add some circuit elements in here to get this thing to 50 ohms. So how do we do that? Well, what's nice about this little program is that we can come in here and play with these numbers. Our goal is to move this dot into the center. And here's why I just love this program, is that we could solve and write an equation, a function to do this. It is very complicated, but this makes it really easy once we get the model set up. So we can come in here and we can increase this inductance, and we can increase this capacitance. And so let's review what we now have. We have an antenna that sits right here. We have a transmission line that's electrically 1.7 inches. We have a parallel capacitance and a series inductance, and that generates 50 ohms. How neat is this? So we have taken our antenna, which presents 80 ohms in J7, and we have transformed it through a piece of transmission line and these circuit elements into essentially 50 ohms. We can sort of verify this by going back to our antenna modeling program, and now we will add a transmission line, and this thing tells us that it's hooked to wire 3, the end of wire 3 right here, to a virtual segment called V4. All right, so now we got a piece of transmission line, and this thing is physically 1 inch, but the phase velocity is 0.58. The next thing we're going to do is we're going to put this network in, and this network is built up of an inductor, a series inductor of 12 nanohenries and a 1 picofarad capacitor. Now we're going to sweep this antenna, so we'll come over here and sweep this guy, and we will produce a SWR plot. All right, so we swept it from 400 megahertz to 500 megahertz. The point of interest that we're interested in is right here, 430. This thing has an impedance of almost 50 ohms and almost no reactance. So we have arrived at this program in 2 methods, and they're fairly close. Something else this program can do is now we can actually plot the field strength. So if we were to look at the field strength along what we call the elevation, or actually looking in from the y-axis to the x-axis, we will see that this thing has a very deep null on if the antenna is pointing off the ends of the antenna. We can now also take a look at we can rotate this plot to give us an azimuth plot, and it turns out that in the azimuth plane, it's pretty darn omnidirectional in the azimuth plane. So guys, this is a very quick overview of the tools we use to design and match antennas. So till next time, adios.